All right. Hi, everyone. Welcome to the next seminar. Today we have my good friend, Andrea Caputo, who's from the University of Tel Aviv and Weizmann. Andrea, many of the audience members will know Andrea. He's worked extensively on a lot of topics from beyond standard model physics, phenomenology, astrophysical searches to new particles, things like this. So he's got a very he's worked on a very large range of topics. He's covered a lot of different ground, but one of the things that he's written some very notable papers on, especially recently, is on searching for these sort of like feebly interacting particles in astrophysical environments, in particular supernovae. So from this great title, I'm sure we're going to learn a lot about supernovae today and new particles. So thanks, Andrea, for being with us, and I'll give you the floor.
Okay, so first of all, thanks a lot for having me here. It's a pleasure, of course, not in person, but anyway. And before starting, actually, I want to say, just feel free to interrupt me at any time. I think that I balanced the talk in order to be like around 40 minutes, so and to leave a lot of space for discussion. So just jump in, and any question that you were afraid to ask in previous talk, just ask me, right? I hope that at the end of the talk, if you pick up any random paper about how to use supernova to test whatever model, you will understand basically all the arguments, okay? And I want to advertise a bit all my collaborators. Okay, some of them, they don't need it to, but most of this work has been done basically in collaboration with Edoardo Vitaliano, with Georg Raffelt, with a lot of nights spent working together, and then Thomas Janka also from MPA in Garching. So just, I think that this audience, given the place, doesn't really need this, but if there are students around, let me tell you also why I'm excited to do what I do and why I do what I do, right? And now the point is that with the standard model of particle physics is a great model, right? Weinberg, Salam, and all the others made a great job in describing natures and all the microscopic physics in the universe, right? But nevertheless, we still have a lot of problems out there in the universe, right? For example, we know that dark matter is out there, 85% of the content of matter in the universe. We don't know what it is, right? So we would like to have some glimpse of that. We know that neutrino masses has to be very small, below the electron volt, let's say, so much smaller than all the other fermion scales. Then we also know that we don't have within the standard model a dynamical mechanism to explain the matter-antimatter asymmetry in the universe. And we have many other problems, like the strong CP problem, the hierarchy problem, flavor anomalies, this day also other problems like W mass, whatever. So we have many indication, okay, that the standard model is not complete. So we have many indication as a community, I think, that there may be an entire new dark sector. Okay, so when you hear about dark sector, you really don't have to think about science fiction. To think about the fact that most of the universe is unknown, right? Basically, if you think about energy content, right? Most of the universe is unknown. So it is very likely that there are a lot of particles out there, right, that live in this dark sector. And our goal, at least my goal during my short career, was I've been doing to try to search for these new particles, also with Kiran actually. So today I will be talking a bit about this, okay? And of course, the question is, how do we look for these new particles, right? In the past, we have been working a lot on collider searches, and I think that we still have to do it, right? I've been working also on, I started actually my PhD working on colliders and how to look, for example, for sterile neutrinos with LHC and then also with future lepton colliders. But I think that no one can deny that it's becoming more and more difficult, right, to go to higher energies or higher intensities. So I think that we have to be creative and we have to look at other things. And what I propose and what I will talk about in this talk is to use astrophysical objects. Here you have also one of my favorite books, is the book by Georg Raffelt. So if you didn't look at it, just take a look. I think it is amazing. And also I want to mention that, the only, if you want, strong indication of physics beyond the standard model, tested right now is really the mass of neutrinos, right? In the sense that we know that the neutrino have masses that didn't have in the initial, theory of the standard model. And we know that neutrino have masses because we observe neutrinos from the sun, right? And the oscillations of neutrinos, right? So I think that the astrophysical objects will play a huge role in the future, and I will tell you how we can use them in order to have more, understanding of physics beyond the standard model, possibly. Okay. I want to start with a general overview, just to give you an idea of how we can use, in general, astrophysical objects, and then I will be more specific and talk about supernovae and tell you whatever I know about supernovae. Okay, there are many ways in which we can actually, look for physics beyond the standard model in stars. First way is that we look at stars. We receive the light from stars, right? So stars basically, they will emit from their surface light, right? Then this light will propagate for parsec or kiloparsec or megaparsec, right, depending on the distance. And then we will get this light on Earth, right, with our telescopes and whatever. Now, in the traveling between the source and us, there could be new physics, like for example, axion or dark photon, that may actually alter the signal and, for example, create spectral distortion. Okay, this is one way in which you can look for new physics. Okay. The second way is that we know quite well how stars lose their energy, right? They lose energy basically because of course, like surface emission of photons, but also like especially volume emission of neutrinos, right? Because neutrinos are so weakly interacting that once that you produce them, for example, in nuclear reaction, then they just escape. And so these are the main basic for many stars is the main energy loss channels, right? So if you now have your favorite particles, let's say if you want to test dark photons here, or scalars, or axion, or Mealy charge, then what you can have is that you have extra energy loss channels. You produce this feebly interacting particle, for example, they will escape. There's an extra energy loss, and so you can alter the life of the star or other observable, like I will tell you. Okay. And then third, if you do produce, let's say, new particles like axions or scalars or whatever, these new particles can actually decay back, okay, into standard model products like electron positron or photons, and then you can pick them up, or you can try to pick them up. If you don't do, you just put bounds, unfortunately. But so these are the main categories, let's say, that I've been working on, and I think that are very useful to have in mind. And in this talk, I will basically focus also on these last two and give you some examples of how we can test motivated models. Okay. Okay. So of course there is when I talk about astrophysical objects, it's a kind of like very vague like a statement, right? There are many stars. Really, we can use them as a laboratory of new physics. Okay, different densities, different temperatures, and I've been working also with Kieran on a variety of different stars. Each of them will have different condition. Okay, and then also different observables, of course, on which you have to focus. Okay, now in this talk, just for a matter of time, I will focus on this corner of the parameter where you see proton-neutron star, and I will talk about supernova. So you have to think about very dense and very hot environment. Okay. So sorry, there is someone that is not muted. Can you? Because I hear some noise.
Yeah, I'll need them. Yeah.
Okay. Sorry. Okay. So in this talk, I will focus on supernovae. Okay. And why is that? Why I chose supernovae? So first of all, because as Kieran said, in the last few months, I've been working quite a lot with Georg on this. And second of all, I think that is a nice example of the interplay between particle physics and astrophysics, because the theory of supernovae was really developed, had a huge push by Jan Bethe, right? He was a nuclear physicist that made huge contribution to the theory of supernova and many other astrophysical theory. So supernova, I think that is a very good ground to understand the interplay that we can have between nuclear physics, particle physics, astrophysics, general relativity, astronomy. Okay. Let me give you, of course, I'm not an astrophysicist. I was trained as a particle physicist. I just like astrophysics, but so I'm not an expert, but let me give you a crash course on the basic physics of supernovae. Okay. So a supernova, a type 2 supernova, okay, is a core-collapse supernova. This I will talk about core-collapse supernova. Is the final stage, is the explosion at the end of the life of a very massive star. Okay, let's say that you have a star with a mass like hydrogen, helium, and then heavier and heavier element inside, where the temperature is larger, right? Then you arrive at the iron that has a maximum in the nuclear binding energy, so it's not favorable anymore to produce any new elements, right? So you're just left with this iron core that has the size of roughly the moon, right? It's very dense, and is supported against gravity just by the generative pressure, okay? Now, at some point, what happened is that the density becomes so large that there are some processes like electron-proton capture that becomes effective, okay? So you start producing neutrinos that escape. So you start lowering the generative pressure, so you cannot keep up anymore with gravity, and then you collapse, okay? You collapse, and the collapse happens in a very short time, like around 1 second, okay? When you collapse, you reach even larger density. The equation of states stiff, nuclear forces become repulsive, and so you bounce back, and you generate a shock that propagates outwards. And so the shock will try to actually explode all the material that was outside. Actually, the story is a little bit more complicated. The shock actually loses energy, and then this was also one of the contribution of Ansel Bethe and all the people, the smart people at the time. And the neutrinos need to actually rejuvenate the shock. And then at the end of the day, after some complicated process, you really rejuvenate the shock, and then you are left with this supernova explosion in which you try to expel all the progenitor material that was here outside, okay? This was really brief. If you want to know more about supernovae, you can look at this CERN colloquium by Thomas Janka. And this slide, I think that was, yeah, I stole it from him, but also from Adam Burrows, actually from Princeton, okay? For, you know, all this is very complicated. There is a lot of nuclear physics. There is general relativity effect that also play a role, okay? So it's all very complicated, but at the end of the day, if you want to do physics beyond the standard model, and if you want to test your own model, what you really have in mind, what you have to have in mind is that at the end of the day, you are left at the end of the collapse of this core-collapse supernovae with what is called the proton-neutron star, okay, PNS. This has a radius of typically like orders of 10 kilometers, okay? Temperatures around 40 MeV, between 30, 40, 50 MeV. It depends a little bit of the progenitor, okay, in the equation of states. And then, of course, like nuclear density, so very large densities. And then it cools down via neutrino emission, okay? So you have to imagine this very dense star that is cooling down just via neutrino emission. And, you know, the material is so dense that actually not even neutrinos can freely escape. They actually diffuse out, scattering over nucleons, okay? Now, this was all very beautiful. The main, the main concept of all this theory were already there in the 80s, basically. And then it's nice to, if you go to the biography of Ansel Bethe, you can read that basically in 1987, he was giving up on supernovae, okay? Because we are physicists, right? So we have to face data, right? And then it would say, okay, I had a beautiful theory, but I didn't have data to test it, right? Russia and United States, okay? And the neutrino signal actually was very clear and was in agreement with the gross feature that you would have expected, okay, from the theory at the time, okay? And sorry, like, is there anything in the chat? Something going wrong?
Yeah, it's just I think I wasn't sure if it was on my end or your end, but I missed maybe about 10 seconds while, okay, so.
Oh, so I stopped, so probably it was my Wi-Fi.
Okay, so, okay, we are getting conflicting things, so it could be an internet, a location-based thing, I'm not sure. No, I mean, so I lost about 10 seconds while you brought up the three images down below, but yeah, maybe
okay,
we'll
so
just carry on.
Okay.
But, yeah.
Okay, let me, but you know, if you have any comments, actually, sometimes I don't see the chat, so just speak out, okay?
Yeah,
But yeah, sorry, let me, for the people that lost me for 10 seconds, the main idea here is that in 1997, we saw the neutrino signal, okay? From a supernova, and the neutrino signal was matching the gross features, of course, like also because the statistics was not very good, to be honest, right? But the gross features were matching the expectation. There's something really non-trivial, okay, if you think about it. For example, the typical energy of a neutron star, okay, this that is left here, is around 10 to the 53 area, right? And if you just do back on the envelope, and in the theory, you expected 99% of it to go into neutrinos. okay? So you could expect the total amount of energy that you was expecting in the neutrino signal. The time scale, for example, of the signal was expected to match like order a few seconds, that is the diffusion time scale. And all these gross features seem to match the naive expectation at the time. Of course, then, it required tens and, 30 years to reach, like, with simulation, really the explosion of the supernovae. Okay, if you have questions about that, just ask me. Okay, but at the time it was already clear that basically the gross feature of the signal were in agreement with the standard neutrino cooling mechanism. Okay, and so people started immediately basically to probe new physics with this kind of supernova. Okay, because it was like it's very simple reasoning, right? It was like, okay, the observation agreed pretty well with what we expected. So if we add more particles, then the signal of neutrinos will be screwed up, right? It will be, for example, shorter because you would lose. I will talk a bit more about this, but the main idea is that if there is other particles, okay, if there are other particles that you can emit, you can lose some of this binding energy in these new particles, and so you would expect the neutrino signal, for example, just to be shorter, right? Because you also you cool down faster your proton neutron star. Okay, so people started immediately, basically, also get the first paper by Georg and Riccardo Barbieri, also with like in the late 80s, like 89, 90s or something like that, right? So, but what I wanted to say,
sorry, Andrea, one second,
yeah.
sorry. So maybe this is in, maybe you said this when you cut out for me, but the timing of the neutrinos in Kamiokande, this gap that you see, you have a cluster of events and then nothing, and then another cluster. It seems more, I mean, you get that in the background as well, but it seems significant in the Kamiokande one. Did they have pinned down what that was due to, or?
No, that's a very good point. So, if you look also, you see, you do see some events instead here, for example, right, in IMB. Okay, so this is a good point. It's actually one of the reasons why some people, for example, like Fear, they were claiming some different scenario for this explosion mechanism that could require, let's say, some gap, in the sense that, for example, in a scenario in which you have that has other difficulties, and if we want, we can talk about that. But there are other scenarios in which, like, for example, you do form a black hole, let's say, then you expect some gap in the neutrino signal for a while. You have some neutrino signal from accretion before, then you form a black hole for a few seconds, you don't have any, and then you have an accretion disk, and then you emit neutrinos, for example. So in that scenario, for example, you can explain this gap. At the moment, the actually best explanation is just some poor statistics, and the measurements were not really good, right? So this was just maybe some oscillations. So if you go into the paper also, they don't really have an explanation for this. Okay, so that's a good point, and something that is one of the first things that I asked when I saw this plot too. But then here in IBM you see some events, for example. So I think that, and I will talk about this, that we will understand if there is something more going on when we will see the next galactic supernova, and we have 3% chance every year to do so. So I think that we just have to wait. Any other question, actually? Okay, so if not, yeah, let me tell you also that despite the fact that we had 30 years of physics beyond the standard model, and model builders using this, there is still a lot of room every time to improve on this and to have new ideas. For example, it was only recently that Robert Bollig and Peter Graham, so this Garching-Stanford collaboration, pointed out that there are muons in supernovae. Okay. A posteriori, this is a trivial statement, because if you look at the Boltzmann suppression, look, the typical temperature of a supernova, as I told you, is like around 40 MeV, right? So if you just think about this, the Boltzmann suppression, and also if you look at the chemical potential, you do expect actually a quite abundant, population of muons, right? Of course, it was not trivial at the time to realize it. So these folks were the first one to realize that you can actually study muonic interaction in supernova, and also neutron stars. Actually, it's the same, right? In this kind of scenario. And so we saw that paper, and then last year we actually considered a different scenario. So in this paper by Robert and collaborators, Will De Rocco, they considered the axion case. So they considered the axion coupling to muons, and then they actually said, okay, what we can say with supernova on the axion coupling to muons, okay? And now what we did instead last year with Georg and Eduardo was to consider a different case. It's a very simple toy model is just a scalar, okay, phi, that coupled to muons in this way with a simple Yukawa operators, okay? It's a toy model that was actually, for us, was motivated by two different reasons. So first of all, we wanted to dig a little bit more in supernova physics and understand what people did. And, to do so, the better way to learn, the best way to learn is just to, as Weinberg say, to jump into the pool, and do some project. So we started with a scalar case that somehow was not considered. And then our interest was, actually my interest in particular, and with Eduardo also, was sparked by the fact that, if you remember last April, there was this announcement by the Fermilab, by Fermilab about the new measurement of the G-2. Okay. Now it depends a bit on, of course, on the lattice group that you ask to, but there seems to be a kind of discrepancy between the standard model calculation of the G-2. Okay. Here I have some diagram that contribute to that at loop level, and then the measurement one. Okay. There is some discrepancy between the two. And so a very simple model in which, with this simple model, actually, you can actually explain the G-2 anomaly. It's very simple. Instead here, in this loop, instead of putting a photon, let's say you put the scalar with this Yukawa coupling, okay? And then if the scalar is below the mass of the muons, basically the contribution is mass independent, right? There is no other scale into the problem but the mass of the muons. And so if you have a coupling of this type, then you actually can explain the G-2 anomaly, okay? So we were interested to this because actually then if you look at the parameter space, as I will show you, if you are below 1 MeV, then cosmology gives you very strong bounds, okay? Because of course, if you have light particles very strongly interacting, they will mess up with cosmology, right? It's pretty easy to understand. If the mass is above 10 MeV, then instead you have like beam dumps and collider bounds that are also pretty strong. But there seems to be a small window between 1 and 10 MeV in which actually this very naive explanation could work, okay? And so what we wanted to see is that if supernova can actually say something on this, okay? And then we started to dig into this, and I will show you what we found, okay? Any question about this up to this point?
Yeah, I guess thinking in the context of that model, is there a particular reason why you might expect, like the new physics to show up in the muon interaction where it was somehow suppressed in the electron interaction? Is there?
That's a very good point. That's very good. You have to be like to work hard with the model building. If you want, we can discuss more about this. There are papers by, for example, Maxim Pospelov or Diego Redigulo. Okay, but like for the scalar, I would say it is a little bit easier. If you do with with vectors, for example, you will always end up, for example, quite natural with coupling also with neutrinos, just because of the doublet, right? For example, with the scalar, you can do some model building in such a way that all the other interaction will be suppressed, and maybe you end up with the one with the muons. But this is why also I'm calling this a toy model, right? In the sense that we didn't dig into the UV completion, in the sense that we defer to this other paper by Maxim and also by Diego Redigulo, Gordon Krianic. But it is true that the most naive expectation will be that, for example, you would couple, if you just do the most naive stuff, maybe a scalar will couple universally, let's say, to all leptons, let's say, right, that are charged some, under some charge, let's say, right, and then probably you will have some bounds from electron searches that are stronger, so you will have to suppress that, right? That's correct. Okay, so but let me show you my results. So this is a spoiler. And see, this is a quite rich plot. This is the mass of the scalar. This is the coupling, this Yukawa coupling, okay? And this is our, let's say, final plot in our in our paper. And I will try to guide you now in all these different colors and region. And so at the end of the talk, I hope that you can basically understand all the basic argument that people use in different guises, like to constrain new physics with supernova, okay? So let's start with a very simple one that is probably the one that you are more familiar with, right? When people talk about supernova bounds, right? What they typically have in mind is supernova is bounds from neutrino cooling, okay? That is what I was telling you. We expect like supernova to cool down with neutrino emission, okay? And we did see neutrino emission from supernova 1987A. Okay, so you can actually look at the duration of the signal, and this duration of the signal will be incompatible with new emission of a lot of new radiation and feebly interacting particles. Okay, so what you have to do typically, imagine that you have your model, in this case, this muon-philic scalar, okay? You have to calculate this energy loss, this is the energy loss per unit mass, okay? In the case of a scalar, it's in this case, it's simple, right? The main process will be basically semi-Compton scattering, right? So imagine that you have some, like some photon scattering over muons and then producing a scalar. Okay, so you can understand all the process here, right? You will have a cross section, sigma t is just the Thomson cross section because it's scattering over the muons. Just rescale with this side that is, it's telling you that there is a Yukawa coupling, so it's different, of course. Then there is y mu, that is the abundance of muons because you have to scattering over muons. And then there is this t to the fourth, that is just the abundance of photons, right? Because you have semi-Compton scattering and then photo production, basically, of the scalars, right? And then just as a back on the envelope, this is just a back on the envelope to make you understand the physics, then you have to compare this epsilon b, this energy loss per unit mass, with this so-called, this is what people usually do, with the so-called Raphael criterion, right? This is not a magic number. Just Georg in 91, what he did was to use some simulation back in the time, okay? And to say, look, based on this simulation, if we put any new extra, cooling, then you will change the neutrino signal. So the cooling, the energy loss should be smaller than this, okay? Actually, what you should really do, and I really don't understand why people don't do that, but most of the time people use, even if they have a supernova model, they will use this Georg criterion, okay? Now, if you have a supernova model, like we did, for example, we had the model by Thomas Janka and the Garshin group. What you have to do, you have to put, I take this model, I use my routine in Python or Mathematica, and you can compute the energy, the emission of these particles within that model. And within the same model, you also have actually the neutrino emission. So in this plot, for example, I show to you the luminosity as a function of time in the simulation, okay? The blue line is the neutrino that goes down with the, with the cooling. It started very large, accretion, and then just cooling down, okay? And then in the red curve are instead the cooling of different models actually that we had in the paper. The solid one is the scalar, but they're all very similar because it's photo production, so the difference at these masses is not large, okay? And so what you do, you basically then compare the luminosity in these new particles with the luminosity in neutrinos, okay? Now, this bottom line here is a so-called free streaming regime, okay? So this is telling you that if you go below this line, so if the coupling is very small, you don't affect the neutrino signal, right? Because the production, of course, depends on the coupling. So if the coupling is too small, you produce very few of these particles, so you cannot compete with neutrinos. So you will not affect the neutrino signal, okay? Then if you crank up the coupling, you are excluded, okay? So this is why this blue region is excluded. But then at some point, you hit another limit, okay? This upper limit here, and this is the limit of the strong trapping regime. Because you have to think about this, you are in a medium, right? When you produce a particle in a medium, when you produce a particle efficiently in a medium, you also absorb the particle efficiently in a medium, okay? So, but at some point, you start producing and get absorbed very, very, very easily, right? So you start to become trapped. And at that point, basically, you can make a couple of arguments. You can talk about radiative transfer, but you can still talk about how much energy you bring out, for example. This is what we did. Okay, but in this regime, it will be pretty different. The physics is a little bit different. When you start having a very large coupling, what happens is that your particle, you emit your particle for a very thin region, right? From where basically you can escape, right? So what you really have to do to determine this line is the following. You compute what is called the optical depth, tau, right? That is just the integral of the interaction rate, basically, okay? And then you individuate when, depending on the coupling and the mass, when is of order 1. Actually, to be precise, 2/3, okay? These basically specify for you a radius, right? This radius here, from which you can escape basically freely, okay? Then you pick that radius, and then you can compute just as a very simple estimate, the surface emission from that surface with Stephen-Boltzmann law. Then you can compare this luminosity with the neutrino one, and then you get this upper bound, okay? So this is actually how you determine this, and this is all the region that is excluded just by Supernova 1987A, okay? Actually, in the literature, if you look at the literature in the last years, there have been a lot of works saying, I mean, also correctly, that, for example, this was pointed out, I think, the first time in a paper by my collaborator, Ruven Essig, in which they pointed out that, of course, a surface emission is never really physical, right? You never have a surface emission. You always have a volume emission, right? That you have to treat well with the optical depth. However, what in the literature has been done, people have been doing some approximation when they did the volume emission in the so-called trapping regime, okay? And in particular, they were considering only radial trajectory. So imagine that you emit a particle, an axion at some point, right? Then this particle have to go out, okay? And then you have to compute this optical depth, how much of that they will go out, okay? So when people computed the volume emission in the past, they did this computation only in the radial direction, okay? But of course, when imagine that you're in a point, in a star, right? And you want to go out, you are emitted and you go out, right? The radial direction is always the easiest path to go out, right? But you will be emitted isotropically, and then there are many other directions, and then you have to average over. And if you do average over, and actually this paper should be, I should submit it by today or tomorrow, so next week you should see it. If you do the average correctly, actually the Boltzmann emission that we use is a very good approximation, much better than the other approximation that you can find in the literature. Okay, so just stay tuned and you will see also why we have all the derivation with radiative transport. Okay, so this concludes basically the first part about neutrino cooling. This is the typical argument that you may heard of. I know that there may be question of curiosity about this, so I think that it's a good moment to stop and to, if there is any question about the cooling argument of neutrinos, just feel free to ask.
Yeah, well, I guess I'm just curious as to how the precise value of the bound is drawn. Is there a statistical meaning to the bound, or is it basically just computing like an inequality, basically?
Yeah, it's just computing an inequality. It's also because, like, at this level, so I wouldn't trust a bound at order factor of few, for example. Okay, because we don't know really the condition of the core of the supernova. The supernova, if you take, let's say, in our paper we discussed this at length. If you have a temperature of 30 MeV or 50 MeV, right, you cannot really say from the data, right, or from just stellar evolution. It can be 30 MeV, but it can be 40 MeV in the core, right? And of course, as you can see also from all the formulas, right, if the temperature is larger, of course, your production will be larger and your bound will be stronger, for example, right? So up to order few factor, there is no, I wouldn't trust it. Up to factor 2, 3, right, let's say, because that will be a factor of 10 in the flux, right? That is what I wouldn't trust. But apart from that, an inequality is really good because you would really expect to shut off the neutrino signal, let's say, at few seconds, right? Because you're really emitting, when you are, for example, in this region, right, your luminosity is hundreds of times larger than the one of neutrinos, right? So you will basically emit all your energy into axions or scalars, sorry. So an inequality is good enough, but there is no statistical meaning also because the observation, they were not really significant, not even to, to understand the energy spectrum, right, and all this kind of stuff. So you cannot do much better than just kind of an inequality at this level.
Yeah, that makes sense. I guess it's
an inequality meaning also that if you go into the simulation and you put his since the beginning, you will see the neutrino signal is shut off. This was already seen in the 90s.
Yeah, the other thing was I was wondering, so this issue with the temperature, is this the reason why you also cut it off at 10 MeV, because there'd be this sort of huge uncertainty about
No, actually here we got it off at 10 MeV just because with this paper, I will show you also some plot at the end in which we go beyond that, right? In this paper, we're just interested to the G-2. And if you go above, here you don't see it, but you will see it, above 10 MeV, then you will have collider bounds, for example, in the region of the G-2. But, like once you fix the temperature, then you can go to very large mass. Basically, if you think about just a thermal distribution, right? If you have a temperature of 40 MeV, the typical medium, like kind of average energy will be a few times that, right? So you will still be able to produce hundreds of MeV particles. Of course, as you said, like if you have 30 or 50 MeV, you can reach higher masses to be produced, right? And that is more uncertain, like it's not that sure. right. That's correct.
Yeah, we have some hands up. Bruce, I think you were first.
So thank you for the talk so far. This is very interesting. Do you have to worry about...
Sorry, I got a call from... Okay, sorry. Go ahead.
Do you have to worry about the volume, the fact that the volume emitting neutrinos and the volume emitting your light scalar are not going to be the same?
Sorry, you got interrupted for a while. You had to worry about the volume, sir?
So, depending on the coupling, the volume emitting neutrinos and the volume effectively emitting neutrinos to infinity, and the volume emitting your light scalar to infinity are not going to be the same. So the energy loss is different throughout the neutron star, and what it's emitting energy to is different. Does that cause issues for the modeling?
So in this regime, not
pressure, right, or to other flow and shock and other things within the volume?
Right, that's a very good point. So in this region that I'm showing you, not. In the other region here that I will show you in another criterion, actually in that can be a kind of an issue, in the sense that in order to be super self-consistent, you would have to do a self-consistent simulation. If you hit the trapping regime, then it happens basically what you are saying, and you know what will happen also that the mean free path will be very short, so you will be competing with neutrinos and photons, and there will be some condition in which basically you will not know how the two surface of let's call them surface. Of course, they are not surface, right? For neutrino, even more, because you have an energy dependent, right, in that case. But then it will depend a bit also the position of the two respect to each other, right, in some regime. Because imagine that imagine that the neutrino one is above the one of the axion, okay, and this is not the case in this case. Then it's more complicated, because the energy that you get at the end of the day is always the energy from the inner side, from convection and all of that, right? And then probably you still will emit it in terms of neutrinos, because just they are like above you in some sense, right? And so you will get neutrinos, right? So there are some regime in which actually this can be more messy. In this regime is never the case, okay? And then in the regime that I will talk about, the surface emission is always happening like around also the neutrino. For example, in this case, for this bound is around 17 kilometers, the surface of the axion. And these roughly coincide with where you see also the neutrino emission in the simulation. That is the one also, if you work in the right coordinate, you will see basically a plateau of this emission of the neutrino going into infinity, okay? That's a good point, but it's more relevant for other kind of coupling, which you can actually, you have to worry about basically radiative transport with two species. There's not something that people do there. And it's something that actually we are trying to work out with Georg, with some toy model.
Okay, thank you.
Any other questions?
Yeah, Marcus had one.
Yeah, so you're showing this bound for a scalar particle. Are there any meaningful differences if it was like a vector boson or a fermion?
Right. So if you have the vector boson, so this region here will look pretty much the same for many particles like vectors, Milli charge, axions. In particular, you will have always this kind of flat bounds on both sides, just because at this point the mass as compared to the typical energy in the core of the star is very low, right? So you will have just, of course, it will be shifted a bit, right? Because you will have some different processes, right? So different processes will have different dependence on the density and properties of the star, but the bound will look very much the same. If the mass is small enough, right, in order not to have any mass effect in the production or absorption, then you will always have this kind of flat bound for all the particles that you can think about, basically, okay? Most of the time, okay? Then for this kind of process, then of course you can have processes like, if decay start to be important, like say, for example, let's say that you take a vector, right? In some region of the parameter space, I would have expected, for example, also to couple to neutrinos. So in that case, for example, you can decay into neutrinos, right? For these masses. And then you will have a different shape because you can decay. And so I would expect the bound to degrade with a mass, right? But for a vector just coupled to muons, or for the axion just coupled to muons, let's say, then it will be basically the same.
Yeah, and so if you have something significantly heavier than this, some sort of WIMP-like particle, then you
then I will show you how the plot will look like. Yeah, I will
Okay.
show you more in the next slides. Yeah, it will be similar kind of to a beam dump in which you have to close because you have to be produced but still have efficient enough, so you will at some point close a bit.
Thank you.
Okay. Okay, great. So after the neutrino signal, I will tell you a couple of addition and go to the fast, like last 15 minutes of my talk, 20 minutes of my talk. There is an important addition in all this. Maybe some of you already noticed that if you have a coupling to muons, you can actually draw a loop. Okay, you don't have to forget about loops, right? I see a lot of papers around in which, you know, you say, okay, let's put to zero this coupling, right? Blah blah. It's very difficult, right? You will always have some loops. So if you don't work hard and really fine tune away some coupling, you will end up with a coupling to photons, for example, if you have a coupling to fermions, right? So you just have, you know, like scalars, a loop of muons, and then you attach just to photons, right? So you have a triangle loop that is very well defined. It's just a scalar. It's the one. It's really similar to the one of the Higgs, right? In two photons. And then if the mass is below the mass of the muons, the mass of the scalar, then basically this loop function is order 1, and then you just have a coupling that is basically alpha suppressed and the mass of the muon suppressed. So it is loop suppressed, of course, but is there. Okay, so you have to consider this additional coupling to photons, and this leads to a very huge phenomenology. Okay, what is this phenomenology? So imagine that you produce this particle in the supernova core, right, that I draw for you here. There are two different ways. Now, imagine that you produce this scalar, okay, this dashed yellow line. Once that you produce it, depending on the mean free path, you can either decay inside, and about this I will talk in length, like in a little while. But then you can also, if the mean free path instead is long enough, you will decay outside, okay? Now, if you decay outside, you will produce gamma rays. Okay, you produce gamma rays. Why gamma rays? Because the typical energy in a supernova, right, is 30-40 MeV, right? So basically, the typical energy will be gamma rays, and then you have that. Okay, so you have this. So if you decay outside, you produce gamma rays, and then I will talk first about this. And then if you decay inside, I will tell you what you have. Okay, if you decay outside, it's very easy to understand, right? Imagine that. Let's take, for example, supernova 1987A. Okay, I will be very fast here because it's easy, I think, to understand, but of course, feel free to jump in. At the time of supernova 1987A, we had a gamma ray spectrometer operating on a satellite and taking data. Okay, so what you can do, you can actually compute the flux of photons that you expect from your scalar. Okay, so in this formula, actually, I have A because I always have in mind, axion, okay, but it's really the scalar in this case. So you can produce the flux of the scalar that you expect to have produced in your core, as I was telling you before. And then you can compute actually how many of them you expect to decay in the path between the supernova and us to form a spectrum of photons in the beam that the experiment was observing. Okay, and then of course this will depend on the flux of the scalar, of the boson lifetime, of course, and then you get this bound here when you compare with observation. Okay, so this is the bound, and of course it's getting worse at low masses because it's a decay. So the decay, if you remember, the decay of the scalar is similar to the one of the pion, right, in the axion. So it will go the decay rate with the mass to the cube, right? So if the mass is very small, the decay length will be very, very long, right? And so most of them, they will not decay between the source and us. So you deteriorate fast, but all this region is actually excluded, okay? Instead of using one supernova, that is supernova 1987A, you can actually use all the past supernova, okay? Because we expect all, there has been a lot of core-collapse supernova also back in the day, right? Up to redshift 1, there is the peak, okay? And this, for example, this core-collapse supernova, they will form what is called the cosmic neutrino background, the DSNB. I think this name was given by John Beacon. So, because as I told you, core-collapse supernova, they produce a lot of neutrinos, right? So you actually expect a background of neutrinos from all the core-collapse supernova in the past. And I don't know if you know this, but it is very interesting. This is Georg that told me this, I didn't know. But this diffuse supernova neutrino background is actually a granted discovery in the next, let's say, 10 years. In the next 10 years, with Juno and Super K, we will have enough data to detect the cosmic neutrino backgrounds from the past supernova. If we don't, then we don't understand something going on, okay? So I think that is very interesting. And then you can have something similar, but with gamma rays. Because now what you do, instead of producing neutrinos, you also produce scalars, but then the scalars in each of the supernova in the past, each of the scalars will decay and will produce gamma ray, okay? And then you can do your computation, of course. This will be, it will depend also on the cosmology, on the core collapse number per comoving volume per redshift interval that you have. Here there is some uncertainty, but the uncertainty is really a factor of 2, so it's not that much. And then you can take this, as we always do, we compare with data, right? We take, for example, Fermi-LAT or COMPTEL data, and we just compare what we have here with the data. So I don't model anything, it's just a very conservative, just compare with data. And then I put this bound, that is this gray region here, okay? This is the region from diffuse gamma rays. So you see here the bound is flat, because of course we are talking about cosmological distances, right? So if the mass is very large, then basically all the particle that you produce, they will have time from redshift 1 to us to decay. Okay, so the bond will be flat. But then also here, when the mass is very small, you start to deteriorate, because actually, the mean free paths start to be, the boosted mean free paths start to be quite large, and so you also lose sensitivity. Okay, but all this region basically is excluded because of gamma rays. Okay, so this I think that is quite interesting. There is actually another addition if you add a photon coupling. That is the fact that you also have to worry about primakoff. Okay, and this I will not spend much time about this because it's not my work. We readapted some work about horizontal branch from these people, Pierluca Carenza and collaborators. And so also this region here, in this region here is excluded by just the number, counting in globular clustering the number of like horizontal branch and red giant stars, basically. Okay. So, but what you notice in this plot is basically that this region here, this G-2 region, okay, is the one, okay, that is basically would explain the G-2 anomaly that I was talking about. So you see that there was still this region that survived all this kind of astrophysical bounds, okay? Because also this gamma ray stuff, at some point they will close here, okay? I don't show the bound here, but they will close. So this region here is really, was allowed. It's not excluded by colliders, it's not excluded by cosmology that will operate below 1 MeV, okay? It was still allowed. But actually, what we propose is a new criterion, that is the so-called explosion energy criterion, for which that region is actually not allowed. Okay, the criterion is very simple, and I will explain to you in length in the last 10 minutes. The fact that when people talk about supernova, they always have in mind the energy loss into neutrinos, right? So energy that goes into neutrinos, and so you don't see it. And there is a reason for that, because we expect most of the energy to go there. As I say, 99% of the binding energy of the neutron star is expected to go into neutrinos. However, 1% of that energy should go into radiation. Now, if your particle decay inside the progenitor, so you remember I had this plot here. Let me go back. I have this plot here, right? If the mean free path is such that the decay happened inside, what you do, you produce a lot of energy, and then you deposit again, you dump it again with in terms of photons, right? Because you decay into photons. And so what you're doing, you're basically affecting the explosion energy of the supernova. And this, of course, depends on the mean free path. But basically what you have that when you compare this blue region, right? This blue region I compare with the energy loss in neutrinos. This typically 10 to the 53 erg. But when you go up in coupling and you actually can decay inside the progenitor, you don't have to compare with the neutrino signal. You have to compare with the explosion energy. And this is typically much, even for supernova 1987A or for normal core-collapse supernova, is only 1% of the binding energy. So instead of comparing with 10 to the 53 erg, you have to compare it with 10 to the 51 erg. So this is why this region is lifted up as compared to the neutrino one. So what we point out in our work is basically that the explanation of G-2 of the anomaly of G-2 in terms of this model is very likely to be excluded by supernova explosion energy. Okay, so this conclude the first part. In the last 5 minutes, I will elaborate more about this criterion. So then actually maybe you can ask whatever question also about this after that I clarify some issues, okay, at some point. Actually, the next step that we did was to, I think this was the last paper that we did with Thomas and Eduardo and Thomas, was to point out that there is a new class of supernova, okay, that is called low luminous supernova, that is particularly interesting in this regard, okay? It's particularly interesting because these supernova are 10 of times dimmer than normal core-collapse supernova, okay? So they are less luminous. The expansion velocity of the external part is lower than usual, 2-3 times. So it means the kinetic energy, V squared. So a kinetic energy is 1 order of magnitude smaller. They measure it just with Doppler shift, right? With the Doppler shift of the material you expect that, then basically you understand which is the velocity of the expansion. And then basically all these observations point to an even lower explosion energy. I was telling you, 10 to the 51 erg, for this low energy supernova, it's 0.1 beta. A beta that is named after Ansel beta is 10 to the 51 erg, okay? So this class of supernova is very, very good to use this explosion energy criterion that we pointed out, okay? We observed many of them. Typically, you saw them like, they are called type 2 supernovae, like sometimes also like plateau supernova, they are called. Of course, this is just a memorandum. When you do this observation, you don't really observe the explosion energy, right? Because what you will observe the luminosity, the temperature, the expansion velocity after the explosion, right? So what people do for many events in many different groups, many different simulations, many different assumptions, what they do is that they take the data, luminosity, velocity of expansion, temperature, nickel and other material abundance. They go back into in their radiation hydrodynamical models, okay? And then they try to fit the data, basically varying 3 parameters: the mass of the progenitor, the radius of the progenitor, the explosion energy of the progenitor. And in all these cases, the explosion energy is very small. Actually, at the moment, I'm working with Thomas, but also with Matteo Cantiello at CCA and Princeton to try to implement also like this modification in this code, like the scalar or axion modification into this code. But what I wanted to say just here is the fact that all this measurement, they point to a very low luminosity. There are actually events that point to a even lower luminosity, 10 to the 49 erg instead of 10 to the 50. We didn't consider this just because these are very few events. While the low energy supernova of 10 to the 50 erg, we have really tens of events. So I think that it's very statistically robust that we do have these events. And what is interesting is that when you take these events, really all the explosion energy and stuff, it really depends on the progenitor stuff. The core doesn't really change much. The core is always roughly the same temperature, roughly nuclear density. So the emission of axion or scalars will not get affected. Okay, this is also a nice point that people really didn't realize. Okay, so and now I focus again on this region. Okay, so again, just to clarify the physics, because this is something that people probably is new. Let's talk about axion in this case, just to go back also to the question, and also because some of you like Kiran and people are more interested to axion. Let's say that you have your axion model. It will be the same like in the scalar case. You produce the axion. If the axion coupled to photon, that is one of the models most of people consider, once that you produce them, you can actually decay back, okay? And if you decay back inside the progenitor, you affect this luminosity criterion, this radiation energy or kinetic energy. So the computation is actually that you have to do is simple. You have to calculate the energy that you dump into the progenitor. This energy will depend on how many particles you produced, okay? And that is here, right? This luminosity for like depending on the radius and the energy. Of course, you have to integrate over the star, over the time shot like of the simulation, and then you have to tell me, I have to write down how many of these particles will decay where I want them to decay. They have to decay outside the core. The main free path should be large enough, otherwise, situation can be more complicated. And then you don't have to decay outside, because otherwise you just have gamma rays, right? So you have to decay inside, and then you can compute this energy, and you can compare this energy with this 0.1 beta, so this 10 to the 50 erg that I was pointing out for low energy supernova. Okay, so for the axion case, for example, for the scalar case, it's really the same. For the axion case, you will have this kind of coupling. You will have the usual processes that many of you know very well, like primakoff, coalescence, blah, blah, blah. Then you have to compute the energy you have to compute this formula. So the primakoff and coalescence goes here, right, in the luminosity calculation. You compute this energy, you compare this energy with the 0.1 beta, and then depending on the mass and the coupling of the axion, you get or don't get a bound. Okay, so this again is the mass of the particle, in this case the axion, but can be very much the scalar, will be very similar. And this is the coupling to the photon. Okay, now you see the solid black line, light region, is the region that is excluded because of this new criterion. Is excluded because of energy deposition and the low energy supernova observation. Okay, just to put you in context, this solid line is really because is like with 0.1 beta and the typical radius of the progenitor, that is the typical one for this low energy supernova. The other lines are just for illustration. It's just to tell you what happens if you change these parameters. But really, you should focus on our benchmark, this solid line. Okay. Now you can see that the neutrino line is this one. It will close up also here. We didn't want to explore because it was not our business. And then this gray line and green line are the gamma ray observation. So you see that our bound actually with this new criterion, it improves by roughly 2 orders of magnitude as compared to the neutrinos. And actually you exclude a lot of the region that was still allowed, like that was also excluded by neutrinos. Okay, so I think that is very interesting. So if you have doubt, also one message of this is that if you have doubts about the neutrino cooling, there was some paper, right, about by actually people also here at Weizmann, right, by Kfir, that casted some bounds on the neutrino bound. We can discuss about that, but if you don't trust the bound, then this is really not about Supernova 1987. It's about an entire different class and is still excluded. Okay, and actually, let me conclude that I did all this curve is like really taking the model, right, and doing all the computation. But if you want to test your model very simply, I came out with a very nice, I think, one zone model. Okay, if you want to do back on the envelope with whatever model you have in mind, just take these parameters. You take a uniform sphere of a radius of roughly 13 kilometers, because this is what I saw in the simulation that was the hot core. A temperature, typical temperature for supernova, 30 MeV, typical density for supernova, nuclear density, and then a time of emission of 3 seconds. Okay, then you do your calculation. It's a very simple model. You can do even analytically somehow. Okay, and then you get as a bound this blue thin line that you have here. Okay, so very, very similar to what you have. Okay, so I think that is quite robust. I think it's also quite interesting. There is a lot to explore at the moment. For example, we are looking also at like nuclear coupling of scalar with nucleons, because this is particularly relevant for dark matter models, especially dark matter that will couple to nucleons, right? Then there will be typically some scalar mediator that couples to nucleons. Depending on the UV completion, at the end of the day, you will have a coupling to photons too. And so my back on the envelope calculation is telling that most of the parameter space is excluded. That typically was not excluded. Okay, so let me conclude here and take questions, of course. I hope that I showed you that supernova physics is a very good example of how you can use many, many different astrophysical observation, gamma ray, neutrino, light curves, and explosion energy to constrain, to put very strong bounds on new physics. I showed you G-2 anomaly, and I showed you also axions. Okay. In the future, the future is really bright, really. At the moment, we are studying really a radiative transport equation with these new particles. We have to be, waiting for the next galactic supernova, okay? Because we have to tell, as I say, there is 3% chance every year to see one. And we have to be ready to tell our experimental friends what we expect. For example, in this case, okay, with this axion in this ballpark, you would expect a very bright signal much before the one that you typically see, okay, with the supernova. Okay, this is a typical signal. And also, let me finish with one last comment, because I always see this and I'm a bit annoyed by this. People talk a lot about this. I don't know if you heard about this cosmic magic axion triangle, right? This is a region that is up here. I forgot to plot the other plot. That is like not excluded by collider, neutrino cooling, or other stuff. I'm pretty much sure, and we show this, that explosion energy do already close that triangle. Okay, so anyway, I want to conclude with this. I didn't see any, I didn't look at the chat. So if there are questions, please feel free to ask now. And thanks a lot for having me with you.
Yeah, thanks, Andrea. Yeah, Victor had his hand up. Do you want to ask Victor?
Yes, please. Could you please show again? You showed the slide with a reference to Primakov process. There was a slide with reference to Primakov process. It's a few slides ago. I don't know, physics letters B something.
This one.
Yeah. Is it really important? Firstly, I need the reference. I'm sorry. I just copied. Is it really important process? More important than direct emission?
No, but in their case, so the point is that in their case, of course, they were looking only at the photon coupling, right?
So it's only for axion. You assume it's
No. The point is that in this paper here, they were looking at axion, right? Yes. But in our case, in horizontal branch, right? Imagine that you always have this scalar coupling, right? You couple two muons, right?
Yes.
But in horizontal branch, you basically don't have muons, right? Because the temperature is very low. So in horizontal branch, the only way in which you, from the modeling from which I started, right, is Yukawa coupling. In horizontal branch, the really relevant process will be the one with photons induced by a loop at loop level. And then, because of the kind of size of the horizontal branch and the observation of horizontal branch, it is actually quite important. But of course, it's more important at low mass, just because horizontal branch temperature is lower, right? But it is really important, the primakoff, also in horizontal branch. Actually, let me also stress this, even in supernova, I didn't say this, but in some region of the parameter space, when you start to crank up the coupling and so the emission is coming from very outside and not in the core, Primakov process is also important in our case, because when you push outwards the emission of the axion, especially in the strong trapping regime, right, you're not anymore in the core, right? You are kind of outside the core. And when you go outside, the temperature drops, and so also the muon abundance drop. So at some point, what becomes also important in our case is really Primakov.
Yeah. May I ask a continued question? Are you considering only axions, or you can consider scalars via Primakov effect?
No, you can consider also scalar. It's Primakov will apply. Yeah.
Primakov apply for scalar. This is my question, because this is I'm specifically interested.
Yes.
I have not seen a reference on this kind of.
Yeah, no. You can go also in our. Yeah. You can go also in our paper.
PhysRef D105, which is on the bottom of the slide. Is it?
Yeah, you can go there, and you can also go into if you also look at Georg book. I think you already find that Primakov for scalars and some comment on that, if I remember correctly.
But this paper contains this information, at least references. Yes,
yes, this information, and how you can recast exactly
it's your paper, yes. So this
is my paper. Yes, this is my paper. Yes. Exactly.
Thank you very much. I will look into it, because we are specifically interested in this process, but for other purpose.
Nice.
Yeah. Thanks a lot. Thank you very much.
Thanks.
All right. Was there anyone else? I think somebody, Dipan.
Yeah, hi. So, this is not the QCD axion, right? So I had two questions. First of all, this is not a QCD axion, right? Like it's ALP. So you're not.
Yeah. In this case, actually, it's a scale.
derivatively.
Yeah, in this case,
coupling.
actually, it's a scalar.
Sure, but that's like when you consider a real axion, if you wanted to constrain like something like a real axion.
Right. You mean
So,
like in this
so
plot
that,
here?
is that like a DFSZ or?
Like
no.
You're completely right. No. The use of the axion line here,
Exactly.
if you don't crank up, if you don't invent some fancy model to lift the mass of the axion, no. This is not.
Okay. So that's
the coupling will be much
second
larger.
question is about the UV completion of this model. So okay, this is a toy model, but like if you really had to do a UV completion with only coupling to muons, I mean, so what would you do? Like, that would look like a pretty weird model, right?
Yeah, sure. But like in this case, for example, you were talking about, because if you're talking about the scalar, we already discussed this with
the scalar,
right?
yes.
If you're talking about the right for the scalar, yeah, I totally agree. But you can do it. I can point you like to the paper by Maxim or Gordon Krianich, like in collaborators, Diego Redigo. You can do it, and people have done it also because it seems to, there are indication. Then of course, like we can take this with a grain of salt. But there is some indication that we don't really understand flavors, right? So
sure, but like
to me, is not crazy, like to given that we are starting to have more and more indication that probably we don't understand flavor, right? G-2 is one of the indication, but it's not. Really
because if you
right?
Because if you couple to the electrons, it would also contribute to EDM, like electron dipole moment, not just.
Exactly, I totally agree. But if you couple to an electron, but even just if you couple to neutrinos, right? For example, if you do a vector, as I was saying, it would be very natural to couple to neutrino, to couple, let's say, to the doublet, right? And then also to neutrinos, right? So in that case, for example, you will have much stronger bounds from cosmology and also from colliders and also from supernovae, actually. And the same apply, of course, to electron, right? But that is not that difficult to model.
Yeah, I understand this point.
Yeah.
Thanks.
But that's totally correct. Yeah, totally good point.
Fred?
Hi, Andrea. Thanks so much for the talk. It was very interesting. I'm just curious, you spoke about the cosmological triangle before. How robust do you think your bounds are there? Like, are you confident that it's either like entirely or mostly ruled out?
It's totally excluded.
Okay.
Let me see if I have some, yeah, okay, yeah, I have it. So this is the cosmological triangle, okay? And this is where our explosion energy apply. And this was not even with low energy supernova, okay? So of course, there is a caveat, okay? That is what I was mentioning also to during the talk. This region is a little bit more tricky than the other region at large mass here, because here you are already in the region of strong trapping regime, okay? So in order to be really, really super self-consistent, you should really do a simulation ab initio, okay? To see what's going on, okay? Also with radiative transport. But given that already with this like, taking the model of supernova, you already see that you deposit a lot of energy, much more than in low energy supernova, okay? To me, looks like really, 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 really unlikely that if you do a simulation, let me recast you in this way. If you do a simulation, the bounds will just improve. I'm pretty sure about that. Yeah, because just these particles are so strongly interacting, right? They are competing with photons. They will compete with neutrinos. What we are saying is that even if you take a model that they didn't take into account the fact that you had a huge interacting particle messing up, even if you don't do that, then this will screw up the explosion energy. If you go back and you put a very strong interacting particle in your simulation, you mess up for sure. And so it will be even more excluded. Then of course people, when they refer to this, and also Georg is a bit annoyed by this, when people refer to this, of course they say, look, maybe it's not excluded, but I think there is no way in which the region is not excluded.
Sure, thank you for that.
Thanks, Fred.
Anyone else? Let's see any. Maybe I just ask one at a sort of maybe more practical level. I mean, you're using these very sophisticated simulations, but at what level are you starting from? What do you get given that I mean, for example, in the neutrino case, it's obvious, I guess you have luminosity as a function of time, energy as a function of time. Well, how much of that simulation output is going into the calculations that you end up doing?
It goes a lot. Like, you know, for this plot, actually, we did a very careful job. Although, at the end of the day, as I showed you, like, really, given the up to factor of few, everything is not sure. In my opinion, a back on the envelope with, you know, if you understand the physics is enough, okay? But when we take the simulation, what you basically take is a radial profile. For example, with this kind of model, you basically need the densities, okay, of muons, and also like actually charged particle when you want to compute the primakoff, because you do primakoff on charged particles. You need a profile of the temperature, of course, right? And you also need, for example, the luminosity of neutrinos to compare with. So you need all this profile of temperature, density, chemical potential, this kind of stuff to compute what you have to compute, right, in your given model. Then you need the luminosity of neutrino to compare with, okay? Actually, in order also to be precise, what we did here, we implemented a lot of like sophisticated, at least in my opinion, given that a lot of people were claiming to use this sophisticated numerical model, then if you do use them, you have to be precise. There are some subtleties that I wanted to mention just because we put a lot of efforts there. In this simulation, you will also find, for example, redshift. That is to say, the fact that you're talking about some solar mass stuff. So when you're very close to that, I mean, what I mean is that the energy that you have at some radius is not the same energy that you will get at infinity. Okay, so because there is some redshift, right? Just because GR effect, right? So when you go into simulation, you actually get this redshift. You have to take that into account when you want to compute, which is the luminosity at infinity, for example. Okay, and so you also need that parameter. You also need, for example, the typical velocity of the medium, because typically the quantity that they are giving you, they are in comoving coordinate. But if you want, again, something at infinity and, you know, in the right rest frame, you also have to take into account that kind of Doppler shift. So these are all the typical quantity that goes into my calculation. But again, if you want to do, I'm always very suspicious when I see papers that claim to have corrected up to factor of few. If you are, okay, of course, if you miss the process and you take that, fine. But if it's just because you did some more sophisticated simulation, whatever, fine. It's not really the point, in my opinion.
All right. Well, if there's somebody else, please just shout out. Don't wait for me to call you. Maybe I'll ask the final question. I guess is you know, we got this 3% chance of having a supernova every year. Do you? I don't know if I had to just ask you to, you know, roughly estimate how much the bounds could improve if you had like a supernova, whatever it is, like the average, like 10 kiloparsecs away or something. Is this does all the added data just help validate the models and make a more precise model, or is there actually would these bounds actually significantly change because you had one?
Well, the one that will like really improve are these one, for example, supernova by gamma rays.
Yeah, right.
Because now we have much better gamma ray spectrometer, right? And if it will be, let's say, something at 10 kiloparsec, 20 kiloparsec, this will be improved by, I would say, and then probably conservative, 1-2 order of magnitude, for example. So this will be one case. And the other one is explosion energy criterion probably will be, you know, very, and also like not in this, just in this mass range, but let's take, for example, this range. This can improve a lot, right? This light region, just because it will have a very clear observation then on the light curves, okay? And then, of course, like you can even opt for a detection. If you don't see a detection, I can imagine this region to be pushed by a factor of few at least in exclusion region. And the neutrino signal, let me say this. The neutrino signal, if we do see, if it will be galactic or stuff, it will be very clear. And if we do see a neutron star, for example, then finally this will, you know, like just stop all this business about saying that this neutrino bound is not robust. That also will be how we'll like just make rock solid this. But because of supernova 1997A, we didn't see yet the neutron star, right? So this is also why people started to claim that maybe that was not a core-collapse supernova in the standard sense. And so this was also but for that also for supernova 1997A, it's just a matter of time. We will see the neutron star. There are already indications for that. So
And I guess, okay, let's get really ambitious and imagine that there was one so close that you saw the pre-supernova neutrinos. Do you know if there's anything you could do during that phase?
In that case, it's difficult, because in that case, the neutrino emission is so efficient. Also, like before the cooling, let's say, right, all the phases before, that will be very difficult to say anything, because it's so efficient that you cannot really compete. It's also the reason why, before the explosion and stuff, you have accretion, right, all these phases. And when you have accretion and stuff, you can do the computation, and it's just scales so rapidly with the temperature, the neutrino stuff, and the density that you cannot really, I think, at least for the model that I have in mind, I don't think that you can really say something. But of course, you will learn a lot about neutrinos that we always forget, but we can always learn a lot about that.
All right. Well, that was a really great seminar. We had lots of nice questions. So maybe I'll just